G'day everyone, my name's Ben, and in this video I'm going to be identifying the issues associated with using baked lighting within the Unreal Engine and guiding you through the process of resolving them. Chances are if you're watching this video, you've just started to import your own static mesh assets into the Unreal Engine, but are unsatisfied with the results. If you've watched the basic level design tutorials provided by Epic, you were likely given the impression that achieving accurate lighting results within the Unreal Engine was an easy process. However, when it comes to baked lighting, that couldn't be further from the truth. The reality is that careful consideration needs to be given to lightmap creation, which can be a time-consuming process. This is especially true when creating static mesh assets that are intended to be modular. If you're a new developer, you may be wondering what the terms baked lighting and lightmap actually mean. Essentially, baked lighting involves pre-computing the light and shadow information prior to runtime, and then storing that information into a separate image file known as a lightmap. For example, if I had a spotlight pointed at the ground, the result may appear similar to this in-game. This is due to the combination of the diffused texture and the pre-computed lightmap, and is not too dissimilar to how layering works in Photoshop. There are three light types within the Unreal Engine: static, stationary, and movable. Only static and stationary lights contribute baked lighting information to the lightmap, whereas movable lights don't, as they're considered to be dynamic lighting and are calculated in real time. Although exclusively using dynamic lighting may seem appealing, as it doesn't require lightmap creation, there is a performance cost associated with doing so. So how do we go about creating a lightmap? Well, the lightmap itself is actually generated by the Unreal Engine, but in order to ensure it produces accurate results, we need to create a second UV channel on all of our static mesh assets, which will be dedicated to the lightmap. The UV mapping considerations for lightmap UV channels differ significantly to those for diffuse UV channels, and I'll explain why in a moment. If you're unfamiliar with the terms UV channel and UV mapping, it's essentially the process that allows us to apply a 2D image to a 3D mesh. In this video, I'll be going through the process in Maya. Before I demonstrate the correct way of UV mapping a lightmap within Maya, I thought it might be beneficial to show some examples of incorrect lightmaps and how they appear within the Unreal Engine. Each example is comprised of 5 modular meshes, which are intended to appear as a single seamless wall structure. If we take a look at the first example, we can see that the result within the lit area is quite good, with no visible seams. However, the unlit area is problematic, as there is no variation in the value of the shadows. The cause of this is no UV coordinate information, or alternatively, UV coordinate information that is located outside of the 0-1 range. Moving on to the second example, we can see that the result within the lit area is quite poor due to the visible seams between the modular meshes. However, the unlit area is looking better in comparison to the first example, as there is now some variation in the value of the shadows. This is a typical outcome when a second UV channel hasn't been created specifically for the lightmap, as the Unreal Engine will use the identical UV coordinate information from the first UV channel. So why is this a problem? Well, when creating a UV map specifically for a diffused texture, it's not uncommon to overlap UV coordinates for the sake of space efficiency, or to use a singular UV shell to achieve consistent scale and to minimize seams. However, both of these approaches are detrimental when creating a UV map for a light map, and will result in light and shadow bleeding. Taking a look at the third example, we can see that the result is almost identical to the second example. Even though a second UV channel was automatically generated by the Unreal Engine upon importing the mesh, the result is still substandard. So why is this? Quite simply, the algorithm isn't taking into consideration the normal direction of the faces, and consequently won't separate and space the UV shells appropriately. In this instance, the second UV channel is essentially a duplicate of the first UV channel, which for reasons previously discussed isn't ideal. Moving on to the fourth example, we can see that the result within the lit area is really good. In comparison to the second and third examples, this is a tremendous improvement, which can be solely attributed to separating the faces with varying normal directions, and then spacing the UV shells appropriately. However, the result isn't satisfactory just yet, as the unlit area still contains some partially visible seams. This is because the edges of the UV shells aren't snapped to the pixel grid. Taking a look at the last example, we can see that the result within the lit area is identical to the fourth example, which is great. However, there is a significant improvement in the unlit area, with the seams no longer visible. This is due to snapping the edges of the UV shells to the pixel grid. This result is as good as we can hope for within the Unreal Engine, and we were able to achieve it with a standard Lightmap resolution of 64 pixels. Okay, so now that we've discussed potential Lightmap issues and how we go about resolving them, I'd like to demonstrate the correct procedures within Maya. Although the following example may seem overly simplistic, the truth is that Lightmap issues are more commonly encountered on hard-edged architectural meshes, more so than organic meshes, due to the abrupt variation in the normal direction of the faces. In preparation for creating the model, I'm going to change the viewport grid size. By default, one Unreal unit is equivalent to 1 cm, so for the sake of simplicity, you should treat one Maya unit as 1 cm as well. Here I'm setting the grid length and width to 1000 units, which is equivalent to 10 meters. I'm going to go ahead and create a polygonal cube. I prefer to have interactive creation disabled and manually input the dimensions, but this is completely optional. By default, the cube will be 1 unit in depth, height, and width. You can zoom in and out on the mesh using the mouse wheel, or alternatively by holding Alt on the keyboard and using the right mouse button. Within the channel box, I'm going to set the width to 100 units, the height to 300 units, and the depth to 30 units. The selected mesh can be framed by pressing F on the keyboard. Alternatively, the whole scene can be framed by pressing A on the keyboard. Panel view modes can be toggled by pressing spacebar on the keyboard. An important consideration with modular meshes is the pivot point. When importing a mesh into the Unreal Engine, it ignores the pivot point set by Maya and instead places the pivot point at the origin, which is equivalent to the coordinates 0x, 0y, and 0z. Due to this, you'll need to offset your mesh to achieve your preferred pivot point location. For architectural meshes, I prefer the pivot point to be located at the front left. Even though the Unreal Engine ignores the pivot point set by Maya, it's still worthwhile to manually set it for other 3D applications. To do this, toggle the manipulator between object and pivot point mode by pressing Insert on the keyboard. Ensure that Snap to Point is active and drag the pivot point to the desired location. It's worth noting that the manipulator can be toggled between Select, Move, Rotate, and Scale modes by pressing Q, W, E, or R on the keyboard. Here I'm performing a quick cleanup on the mesh by deleting the history, freezing the transformations, and renaming the object. The quad view is no longer required, so I'm switching to a split view that contains the perspective viewport and the UV editor window. When I created the polygonal cube, Maya provided automatic UV mapping. Since the dimensions of the mesh have changed, the UV coordinate information is no longer accurate and will need to be deleted. Earlier when we discussed potential Lightmap issues, I stressed the importance of snapping and spacing on the pixel grid. So how should the grid size be calculated? Well, you want to divide 1 by the target Lightmap resolution. By default, the Unreal Engine uses a Lightmap resolution of 64 on imported meshes. However, in this instance, I'll be dividing 1 by 32. So does this mean that I'll be using a Lightmap resolution of 32 within the Unreal Engine? Well, not necessarily, but it's a better idea to target a smaller Lightmap resolution than what you think is required, as it will gracefully scale upwards, whereas the same can't be said for scaling downwards, which will likely cause issues with light and shadow bleeding. I'm going to start the UV mapping process for the diffuse UV channel, which the Lightmap UV channel will be derived from. Holding down the right mouse button over an object will bring up the selection mode menu. I'm going to switch the selection mode from object to face, and then select the front and back faces. You'll need to hold down Shift on the keyboard for multiple selections. To orbit around the selected mesh, hold Alt on the keyboard and drag with the left mouse button. I'm going to planar map the selected faces. This can be done by going to the Create UVs menu and selecting the planar mapping option. Be sure to click on the settings box, as the default settings will not be appropriate. In this instance, I want to project from the Z-axis and enable the option to keep the image width and height ratio, as this will ensure correct scaling. Once again, I'm holding down the right mouse button to bring up the selection mode menu. I'm switching the selection mode to shell and temporarily moving the projected faces out of the 0-1 range, which is the dark grey quadrant. As I mentioned earlier, if the UV coordinate information is located outside of the 0-1 range, it will be ignored by the Unreal Engine and consequently problematic. The planar mapping procedure is identical for the remaining faces, with the exception that the most appropriate projection axis will need to be selected. The scaling on the top and bottom faces is larger than the other faces. This is because Maya automatically scales the projected faces to the bounds of the 0-1 range. Not to worry though, I'll be manually fixing this shortly. Here I'm enabling the shaded UV display. Since the planar projections are performed in a single direction, some of the projected faces will be flipped, indicated by the red shading. These will need to be manually corrected, otherwise the diffuse and lightmap information will be displayed on the inside of the mesh instead of the outside. Now that all of the faces have been correctly projected, I'm going to switch the selection mode to Edge and start sewing the UV shells together. Doing so will minimize the seams when creating a diffuse texture, but isn't ideal for a light map. Modifying the pivot point location is essential to correctly aligning the UV shells to the grid and to each other. In order to do this, toggle the manipulator between object and pivot point mode by pressing insert on the keyboard. Ensure that snap to points is enabled and drag the pivot point to the desired location. Once this is done, press insert on the keyboard once more, disable snap to points, enable snap to grid, and move the UV shell into place. I encourage you to become familiar with this process as it's used frequently when moving and scaling the UV shells. Using the same procedure as previously discussed, I'm manually aligning, scaling, and sewing the top and bottom faces to the main UV shell. Here I'm ensuring that all of the UV coordinate information is located within the 0, 1 range. At this point, the UV mapping for the diffuse UV channel is complete. To keep things organized, I'm going to go to the UV set editor and rename the first UV channel. If the UV set editor has no UV channels listed, ensure that the object is selected within the scene. Moving on to the Lightmap UV channel, I'm going to save myself some time by copying the diffuse UV set and using that as a starting point. This can be done by going to the Create UVs menu, followed by the Copy UVs to UV set submenu, and then selecting Copy into New UV set. Within the UV texture editor, the UV sets can be switched via the UV sets menu. Ensure that the Lightmap UV set is selected. Here I'm switching the selection mode to face, and I'm going to select and separate each face that has a hard edge. Once that's completed, I'm going to start the process of snapping the UV shell edges to the grid, as well as spacing the UV shells appropriately. If the previous contents of this video have put you to sleep, now would be the time to grab a coffee or energy drink and start paying attention, as this is the business end of the whole process. Ensure that Snap to Grid is enabled and change the selection mode to UV. Select the UVs along each individual edge of the UV shell and move them until they snap into place. This will likely result in a non-uniform scale, but that's perfectly fine, as the resulting distortion will be minimal and the benefits of snapping the UV shell edges to the grid far outweigh the benefits of maintaining uniform scale. Repeat this process for each UV shell. So how much space should be between each UV shell? At minimum, there should be one grid space, which is equivalent to 1 pixel with a Lightmap resolution of 32, between each UV shell. Ultimately, if the mesh is simplistic enough that this number can be increased, then it should be, as it minimizes the likelihood of issues occurring. In this example, there are 2 grid spaces between each UV shell. At this point, the UV mapping for the Lightmap UV channel is complete. Switching between the two UV sets, the contrast in UV mapping considerations is evident. For the diffuse UV channel, there is a singular UV shell with uniform scaling that isn't snapped to the grid, whereas for the Lightmap UV channel, there are multiple UV shells with non-uniform scaling that are snapped to the grid. As a bonus, I thought it may be beneficial to demonstrate the procedure for adding a collision mesh within Maya. Although the Unreal Engine has the functionality to generate collision meshes, it can be a quicker process in Maya depending on the complexity of the mesh. It's as simple as duplicating the original mesh and then renaming the duplicate with a prefix of UCX_. All that's left to do within Maya is export the mesh, which can be done by going to the File menu and then selecting Export All. Select FBX as the file type and then ensure that Smoothing Groups, Smooth Mesh and Triangulate are all enabled under the geometry settings. In order to test the mesh within the Unreal Engine, I'm going to create a new project based on the first-person template. Once the Unreal Engine editor has finished loading, the next step is to import the mesh. This can be done by clicking the right mouse button within the content browser and then selecting Import. In the FBX Import Options window, Auto-Generate Collision, Generate Lightmap UVs, one convex hole per UCX, and Import Materials and Textures should all be disabled, as this will undo our efforts in Maya. I'm going to go ahead and create a basic material to apply to the mesh. Typically, lightmap issues are more evident on non-textured materials, so even if you intend on using a complex material on the mesh, it's not a bad idea to have a basic material for testing purposes. Within the content browser, double-click on the mesh thumbnail with the left mouse button to open the mesh within the static mesh editor. Here I'm applying the previously created material and double-checking that the collision, pivot, and UV coordinate information have all been successfully carried over from Maya. The default lightmap resolution of 64 is fine for now, and should only be increased if the baked lighting result isn't as detailed as desired. I'm going to place the mesh into the scene and duplicate it until there are 5 instances. This can be done by holding Alt on the keyboard when manipulating the mesh. Once the meshes are in place, I'll set the lighting quality to production and then build the lighting. Taking a look at the result in-game, the lid area is perfect and as desired. However, upon closer inspection of the unlit area, there are partially visible seams within the shadows. Now, considering that a typical situation wouldn't have modular meshes that are this small in size, or materials that are this basic, this outcome may be perfectly acceptable. However, the result can be improved further with a couple of compromises. Within the world settings, there are two lightmass variables that can be modified to improve the result: static lighting level scale and indirect lighting smoothness. So what are the compromises associated with changing these variables? Well, decreasing the value of static lighting level scale will drastically increase the time it takes to build the lighting. In addition to this, increasing the value of indirect lighting smoothness will decrease the overall sharpness and detail of the shadows. In this instance, I'm happy with the compromises, and I'm going to set the static lighting level scale to 0.1 and indirect lighting smoothness to 2, and then rebuild the lighting. Back in game, the result for the lit and unlit areas is perfect, so modifying the world settings certainly did the trick. On that note, I'd like to thank you for watching this video, and sincerely hope that it helps you with your level building endeavours.